A pleasant day to each and everyone, and to you, ma'am. We are tasked to discuss Chapter 1. Since Chapter 1 is composed of 4 subtopics and every group has 8 members, that's why we decided to discuss every subtopic by pair. For Chapter 1.1, it would be Armero and Magaway. Chapter 1.2, Reyes and Puco. Chapter 1.3, Morsin and Diparini. Chapter 1.4, Natividad and Ruby.
Let's proceed to chapter 1.1. What is organic chemistry? Organic chemistry is the chemistry of the compounds of carbon. Organic compound has remarkable features since it is involved in the chemistry of carbon and few elements like hydrogen, oxygen, nitrogen, sulfur, and halogens such as fluorine, chlorine, bromine, and iodine. In the Earth's crust, it is abundant of different elements. However, carbon only belongs to 0.9% of it. Out of 100 elements on the periodic table, why do we need to pay attention to carbon when it is only 0.9% among the most abundant element in the Earth's crust?
So we have 3 reasons why we need to study carbon compound. First, it is historical, in which scientists believe that organic compound came from living organism, while inorganic compounds are those from non-living matter such as rocks. Vital force, it is a theory, was only possessed by living organism which is necessary to produce organic compounds. Chemists believe that they could not synthesize any organic compounds by starting only in organic compounds. However, a German chemist, Friedrich Willer, heated aqueous solution of ammonium chloride and silver cyanide, which this two is an organic compound and it produces urea. It is an organic compound that can be found in urine.
Second is the sheer number of organic compounds. That there's approximately 85% of all known compounds synthesized and discovered by chemists are organic compounds. Specifically, there are 10 million organic compounds that are discovered and an estimate of 10,000 new ones were reported yearly, while for organic compounds it has 1.7 million of it.
The third, it is significant in the study of biochemistry. Biochemistry, it is a branch of science that explore the chemical process within related to life, where in biochemistry, almost all of the important chemicals in living system are organic compounds, namely the carbohydrates, lipids, proteins, enzymes, hormones, vitamins, nucleic acids, or the DNA and RNA.
So in the image shown, we have the properties of organic and inorganic compounds which makes them different from each other, such as for organic compound it is entirely covalent while organic compounds have ionic bonds and so on.
We have takeaways. It is very important to study organic chemistry because it tackles the vital processes of life and all the chemical reaction related to life, including biochemistry, pharmaceuticals, and industry. That will be all for our part. Thank you for listening. Let's proceed to chapter 1.2.
Good day, I am Caroline G. Reyes, and for chapter 1.2, we'll be answering the question, where do we obtain organic compounds? So there are 2 principal ways in which chemists obtain organic compounds. First is by isolating them from nature, and the second way is by synthesizing them in the laboratory. For isolating them from nature, living organisms are basically chemical factories. Each of these organisms make thousands of organic compounds by a process called biosynthesis. So how do we obtain organic compounds from them? Organic compounds from these biological sources are isolated by solvent extraction and then followed by purification. Here are some examples of organic compounds obtained through this method. From these biological sources, they are again converted naturally into petroleum oil, natural gas, and coal, which are 3 important sources of organic compounds that nature supplies us with.
Synthesis in the laboratory. Compounds made in the laboratory are identical in both chemical and physical properties to those found in nature, assuming, of course, that each is 100% pure, because there is no way that anyone can tell whether a sample of any particular compound was made by a chemist or obtained from our nature, just like, for example, pure ethanol. Made by chemists has exactly the same physical and chemical properties as pure ethanol prepared by distilling wine. Vitamin C. Same is true for ascorbic acid or vitamin C. Well, there is no advantage in paying more money for vitamin C obtained from our natural source than for synthetic vitamin C because the two are identical in every way. The majority of the more than 10 million known organic compounds are purely synthetic and do not exist in living organisms. For example, many modern drugs, Valium, albuterol, Prozac, Zantac, Zoloft, Lasix, Viagra, and Enovid, are synthetic organic compounds not found in nature. And even the over-counter drugs, aspirin and ibuprofen, are synthetic organic compounds not found in nature. Taxol, a story of search and discovery. In early 1960s, the Natural Cancer Institute undertook a program to analyze samples of native plants materials. Would prove effective in fight against cancer. Tested an extract of the bark of the Pacific yew, Taxus brevifolia, a slow-growing tree found in the old-growth forest of the Pacific Northwest. Effective in treating certain types of ovarian and breast cancer. The structure of the cancer-fighting component of yew bark was determined in 1962, and the compound was named paclitaxel or Taxol.
This structure of paclitaxel was first discovered in the Pacific yew tree Taxus brevifolia in 1962. Taxol is one of the best plant-based cancer treatments, and below is a short explanation on how the drug effectively controls their spread. Originally, Taxol was extracted from the bark of the Pacific yew tree, in which a single dose required the sacrifice of a 100-year-old tree. More recently, however, investigators found that the needles of some related trees and shrubs contained precursors of Taxol from which complete Taxol could be synthesized. All in all, by synthesizing Taxol in the laboratory, the compound Taxol has become more accessible to the public.
Good day, I am Raven Morrison, and this time I will be discussing the chapter 1.3, How do we write structural formulas of organic compounds? So what is a structural formula? Structural formula shows all the atoms present in a molecule as well as the bonds that connect the atoms to each other. So say for example, here we have the ethanol. Ethanol has molecular formula of C2H5OH. So as we can see in its structure, left side of the carbon contains hydrogen attached to it. In the middle side, we have two hydrogen, and in the right side, we have the alcohol. That's why it is called ethanol. We also have here the zigzag structure of ethanol. Next one is the Lewis model of bonding. It is how the carbon forms four covalent bonds that may be various combination of single, double, and triple bonds. Moreover, Lewis dot structure also represents the valence electrons as dots. Say for example, the carbon dioxide valence electrons, and those four valence electrons will surround the carbon itself as dots. So the next one, we have the valence shell electron pair repulsion or VSEPR. So what is the meaning of this? This will be used to predict the molecular geometry of a compound based on their valence electrons. So we have here the ethylene structure. So this is considered as planar since it contains double bond and has 120 degrees bond angle. So ethane is considered as tetrahedral because it contains only single bond, and it has 109.5 degree bond angles. And acetylene is considered as linear because it has triple bond and has 180 degree bond angles. So the next slide will be tackled by Mr. Michael De Parini. Thank you.
Hello, I'm Michael Patrick K. De Parini, and I will discuss to you the important things that you should remember when you create your first structural formula. This is about how many covalent bonds, or to simplify it, how many elements can you connect with other elements. So here we can see carbon, nitrogen, oxygen, hydrogen, and halogens. Carbon normally forms 4 covalent bonds and no unshared pair of electrons. On the other hand, nitrogen normally forms 3 covalent bonds and 1 unshared pair of electrons. As we can see here, 3 hydrogen bonds near the nitrogen. It is usually shown as 2 dots near the element. Meanwhile, oxygen has 2 covalent bonds and 2 unshared pairs of electrons. Hydrogen has only 1 covalent bond and has no unshared pair of electrons. And the last one, halogen, forms 1 covalent bond and has 3 unshared pairs of electrons. To show the unshared pairs of electrons, same as nitrogen, you just put a pair of dots near the atom. Now, to give a simple example on how to create a Lewis structure for each molecule. As you can see here, I did this on purpose to make it look incomplete so that we can answer this. Let us count how many carbon atoms there is. And it is missing another one. About the hydrogen, there are 1, 2, 3. Oh, it lacks 3. We should complete the Lewis structure for each molecule by adding unshared pair of electrons so that each atom of carbon, oxygen, and nitrogen has a complete octet. To complete this, we just need to add another carbon atom and put 3 hydrogens near it. And after that, congratulations, you have done it. Very good. Using the VSEPR model, predict all bond angles in each molecule. Since it is only carbon and it is very simple, we can just copy from the internet and poof, here we go. At the next juncture, Miss Micah Ruby and Mr. Prem Natividad will discuss chapter 1.4.
Functional groups play a significant role in directing and controlling organic reactions, as well as providing means in distinguishing compounds, as it classifies organic compounds into families. It is basically a group of atoms that functionalizes a compound, all the while giving molecules similar properties. There are 6 common functional groups, and I will be discussing the first 3. My name is Micah Vanessa B, and welcome to my TED Talk. Sure. So the first functional group is the alcohol group. Alcohol refers to the compound containing the OH hydroxyl group. Depending on the position of the OH group on the chain, alcohol can be categorized as primary, secondary, or tertiary. There are 2 different positions that an oxygen atom can be bonded to a carbon chain. These are either to an end carbon or the middle carbon. So here are some examples of alcohol. Second functional group is the amino group. Amines are organic compounds derived from ammonia or NH3. They're classified according to the number of carbon atoms directly bonded to the nitrogen atom. Primary amine has 1 alkyl group, secondary has 2, and tertiary has 3. In the primary amine, the nitrogen is bonded to 2 hydrogen and 1 carbon group. In the secondary amine, nitrogen is bonded to 1 hydrogen and 2 carbon groups. In the tertiary amines, nitrogen is bonded to 3 carbon groups. Here are some examples of amine. The third functional group is the aldehyde.
Good day everyone, I am Primar Binatividad and I will be discussing the 3 functional group, specifically the ketone, carboxylic acid, and carboxylic ester. In our previous learning, we know that ketone is a carbonyl group, which means a carbon double bonded to an oxygen. The general formula of it is C double bonded to O. As what you have noticed in the table above, ketone has a suffix "-on". Naming ketones are the same way as our other hydrocarbons, except that "-on" ending is being used. The same way is carboxylic acid and ester. Carboxylic has a general formula of COOH composed of carbonyl and hydroxyl, and in ester, ROOR, where R can either be a hydrogen or a carbon chain. Carboxylic acid and ester has also suffixes. In carboxylic acid, it has a suffix of oic acid or carboxylic acid, and in ester, it has a suffix of oit. And in naming these 3 functional groups, we should always follow the general rule, numbering the longest carbon chain and choosing the lowest number possible. And that's all for today. I hope you learned something from this lesson. God bless us all.